Hello everyone, this is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering College. Here we are going to discuss about a few important topics from nonlinear data structures, which is trees and graphs. Let's have a look. So what do you mean by nonlinear data structure? Nonlinear data structure is a structure where the data is not stored in a sequence. That is, one data part is related to more than one data part, right? So there are two types of nonlinear data structures. One is trees and the other is a graph, right? Let's have a look at both of them. Then the basic difference between linear and nonlinear is, in case of linear data structure, as I said, one data point is related to another data point. A simple diagrammatically, I can say, if you feel array as a linear one, the elements are stored in contiguous memory locations. The other linear structure is linked list, where the data, even though it is not placed in contiguous memory locations, that is, the data is scattered all over the memory, but first each and every node will be linked to only one another node, not more than that. So that's why we call array and linked list to be linear in nature. Coming to nonlinear data structures, right? Nonlinear data structures, trees and graphs. If you look at trees, so parent node will be there, which is connected to its children, and these children may have children of their own, right? You can see that the first node is related to more than one node. Here it is having 3 children. Node 3 is having 2 children. More than one node you are related to. One more type of nonlinear is a graph, right? Let's have a look at a graph, small graph, right? So if A, B, C, D are the vertices of a graph, then you can clearly see that A is having 3 neighbors, C, D and B, right? So when you talk in terms of C, it is related to A, B and D, 3 different nodes. So there is no one-to-one cardinality in case of nonlinear data structures, but it is the cardinality is 1-to-1 in case of linear data structures. That is the basic difference between these two types of data structures, right? So the next one, let's start with the basic tree structure, as we are concerned with nonlinear data structures right now. So have a look at this, a simple picture which I have brought over here. Tree animals. They can be reptiles or mammals, right? Coming to reptiles, they can be lizard, snake or a bird. Mammal, different categories, right? So you can see a structure which is a top to down structure from the root to the leaf nodes. The node which do not have any children is nothing but a leaf node. Top down structure you can see. And if go for the applications of the trees, you can see that any organization chart, any file system in your drives, like your C drive, you are working on your C drive will have many folders, say like movies. In your C drive, you will have photos. You may have a simple ones I'm going with, right? So you have music. Like within movies, you can have n number of movies and loads more. So that itself, file system is nothing but a structure of tree in itself, right? So coming to the terminologies which we use in terms of trees, the root, a node which do not have a parent is a root node, right? A is the root node which do not have any parent. Coming to siblings, the nodes which share same parent are siblings. For example, B, C and D. All 3 have A as their parent. So you can call A as the root, as the parent of B, C, D. Let me take one more example. E, F. They have B as parent. So E and F are siblings. right? G and H are siblings. I, J, K are siblings. But you cannot claim that F and G are siblings because the parent of F is B and whereas G is C. Okay, so siblings are the nodes who share same parent. Okay, internal nodes. Any node who have at least one child is internal node. In this picture, I have colored internal nodes with blue. So A is having children, C is having children, B and F, they are having at least one child, at least one. They are having. So they are known as internal nodes. External nodes are the nodes which do not have children. They are also known as leaves, like E, I, J, K, G, H, D. All these are leaf nodes which do not have children. Then ancestors. Ancestors are nothing but parents, grandparents, grandparents are nothing but ancestors. In point of view of E, B is parent, A is grandparent. P and GP comes under the category of ancestors. In point of view of say J, F is parent, B is grandparent, A is grandparent. All three are ancestors. A reverse of that is descendants, right? So child, grandchild, grandchild karke. So in point of view of B, F is a child, I, J, K are grandchildren, right? So they are the descendants, right? What is it then? Let's talk about the last terminology, which is a depth of a node, right? So depth of a node, when you talk about it, so if a node is M, then its length of the path from the root till M is nothing but the depth. Okay, say if we are talking about F. So from the root, first 2, so depth is 2. Okay, so depth of say F. For example, depth of H you want to calculate. Depth of H is from the root. Always start from the root, guys. So A to C, C to H, which is 2. So this is how we are going to calculate depth of any node, right? So next terminology is the height. Height of a node is the number of edges of the node to the deepest leaf. Okay, so for example, consider what is the height of node B to the deepest leaf is, even though E is a leaf, but it is not the deepest one. I, J or K stands as the deepest leaves of node B. So its height will be 2, right? Coming to the degree of a node, its children. The number of children it has is nothing but the degree of any node. So degree of say F is 3, it is having 3 children. Degree of B is 2. By default, a degree of all leaf nodes is 0 because they will not have any children, right? So degree of the tree is maximum number of its nodes. That is the total number of nodes that originate from it, right? So that will be the degree of a tree. So the degree of A is 3 over here, right? Coming to the subtree. Subtree is nothing but the tree which is having node and its descendants collection is nothing but a subtree. For example, the one which I have highlighted in violet, you can see it is nothing but a subtree, which is headed by C and its children are G and H. It is one of the subtrees. Or you can also have another subtree, say B is headed and this is the subtree, right? So headed by B, which is having children EF and grandchildren IJK, right? So this is nothing but the concept of subtrees. Next, the basic properties, that is the number of nodes, the height, the root node, leaves, interior nodes, exterior nodes, ancestors, degrees, all these things will be the basic properties of any tree. Next, a class of a tree where we put a restriction saying that it can have maximum of 2 children is nothing but a binary tree, right? Have a look at this picture. As a tree is a top-down structure, from the root if you start, every node will have a maximum of 2 children, or at one child or 0. That is, the number of children will be either 0, 1 or 2. Is nothing but a binary tree. Right? So the variants of the binary tree are full binary tree, complete binary tree, perfect binary tree, balanced binary tree, left skewed and right skewed binary tree. Let's look at each and every one. So full or strictly binary tree. A binary tree where every node except the leaf node have either 0 or 2 children, then we call it as full or strictly binary tree. That is, having at least having one child is ruled out. Such a case is known as full or strictly binary tree. In case of a strictly binary tree, so the number of leaf nodes is 1 more than the number of internal nodes. So have a look at this picture. You have 3 leaf nodes and 2 internal nodes, right? So this is full or strictly binary tree. Next, complete binary tree. A node where this is basically a binary tree if all levels are completely filled except the last level, and even the keys are as left as possible. Such a tree is complete binary tree. For example, if you have a tree in this way, 2 children, 1 child and 1 child. So this is not a complete one, because the right child of this node, say X node, is not present. So this is no longer a complete binary tree, right? So a binary tree is called as a complete binary tree if its all levels are filled except the last level, and even in the last level the elements are filled from the left. Then we call it as a complete binary tree. So if you talk about levels, the root will always be at level 0. The next is its children will be at level 1 and its grandchildren will be at level 2. Okay, so the number of nodes will be 2 to the power of d plus 1 minus 1, where d is the depth of the tree, and the number of leaf nodes is 2 to the power of d. Please remember these values, terms, guys. The number of nodes in a complete binary tree and the number of leaf nodes in a complete binary tree. Okay, so then what is perfect binary tree? A perfect binary tree is in which all internal nodes have 2 children and all leaf nodes are at the same level. All internal nodes, that is 8, 4 and 10. All internal nodes must have 2 children. Okay, and all leaf nodes are at same level. If I say that here 2 is having 2 children, then it will no longer be a perfect binary tree. For a binary to be perfect in nature, all internal nodes must have 2 children and all leaf nodes at the same level. So then height of a perfect binary tree, if it is h, then the number of nodes will be 2 to the power of h minus 1. Okay, please remember these terms. Next comes balanced binary tree. A binary tree where the balance factor is either minus 1, 0 or 1. I'm talking about balance factor. What do you mean by balance factor? That is nothing but the difference between the height of left subtree and the right subtree. For example, consider a node 3. The height of its left subtree is 2, whereas right is 1. The difference is 1. Fine. The root node, the height of its left subtree is 2, right subtree is 3. Difference is minus 1. Fine. You need to calculate for all. By default, the balance factor of leaf nodes is 0. Balance factor of leaf nodes is 0. Right? So if the balance factors of all the nodes is either 0, 1 or minus 1, then we call that as a balanced binary tree. Right? So the right side figure, if you can see, if you check the balance factor of the root, the left subtree length height is 1, Right is 3, the difference is -2. So this is not a balanced one, it's an unbalanced one. Okay, then left and right skewed. If in any binary tree, if it is only the left subtree, it does not have any right child, right grandchild, grandchild, whatever version you take. If it doesn't have any node in the right side, then we call it as left skewed. Contrary to that, if a binary tree where there is no left child, neither left child, neither grandchild, left grandchild, no one in the left side, then it is known as a right skewed tree. Okay, so these are the variants of binary tree. Then how to represent a binary tree? We can represent it using arrays as well as linked list. Then how to represent it using arrays? Always give the index values. Arrays have index values, right? Root and index value 0 and its children with the following index values as 1, 2, 3, so on. Whenever you go for the next level, start giving the index values 3. If 4 value 4 have a right child, its index value would have been 4. Next is the right child of 8, which is 10. It is not having any left child, but its index value will be 5. In future, we never know if someone inserts a left child to 10 or a right child to 4, they may come. At that time, we cannot create any space for it. So, we provide the space for it. And at an index value 6, the right child of 10. So, in this way, index values, arrays, have a look at the array which I have given, guys. Right? So, the maximum size of so first of all, before assigning or inserting the data values of a tree in an array to store, we need to give the size of the array which I'm talking about, right? So the size of the array will be 2 power d plus 1 minus 1. That is the depth of the tree. That is the maximum size required by a binary tree of depth d. Okay, this is how we can store the data, the binary tree data in a array. The basic disadvantage is height. If the height is growing and internal nodes are not filled, wastage of memory will be there. Insertion and deletion of a node is highly difficult. Advantages: random access is possible at any point of time. You can traverse to any node, right? So to overcome the disadvantage, you can go with the linked list representation of the trees using a double linked list. I hope you remember this one. This is the structure of double linked list, where every node will have 3 parts. The primary one is the data part. The left side is left child's address and the right is right child's address. Have a look at the representation. If any node is not having any child in the left or right side, its address part will be none. Very simple, right? Like this, we can even represent the trees using linked list. Okay, so the advantage is height of the tree need not be taken. So in arrays, to decide the size of the array, we need to know the height or depth of the tree beforehand, which is not required in case of linked list, as we are going to dynamically create the nodes if we insert and remove the nodes if we delete, right? So memory wastage will be not be there, and insertion and deletions are quite easy. Coming to the disadvantage, direct access is not possible. Always you have to start with the root node, right? We have to start with the root node, and a bit of memory will be wasted to store the address of the left and right children, right? As the data is not stored in contiguous memory locations, we need to hold the address of the left child as well as the right child also. So as we are using double linked list to represent a tree, so 2 parts out of 3, 2 parts will be used to store the addresses, which is wastage of memory. Okay, so then have to traverse, have to run in this binary trees. So unlike your linear, we have three different methods we do traverse. One is a in-order traversal, where we are going to travel from left, the root, and the right. This is the order. So it is in case of binary search trees, and if you go for in-order traversal, you get the list in ascending order. Very simply, you can get the ascending order list. Let's see how we can represent. So if this is the binary tree I'm talking about, first of all, start from the root, always from the root. Left side, 4 is still having a left. Go towards left. 2 is not having a left. So insert 2. Now go to the root. Right, 4. Then 4, then go to its right child. So is it having any left? No. 6 is there. Print 6. It is not having any right. Go to the root, which is 8. Left part of 8 is done. So print the root 8. Go to the right part. When you go to the right part, 10 is having a left part. 9. 9 is not having any left part. So print 9. 9 is not having any right part. So the left subtree of 10 is done. Print 10. Then go to the right side of 10. 11 is there. It is not having any left child. So print 11. Then as it is not having any right child, end of the story. This is the in-order traversal of the given binary tree. The next traversal technique is preorder traversal. If you want to go with preorder traversal, you need to traverse the root first, left, and right. It is useful to represent expression trees. Representing an expression in terms of a tree, preorder is very useful. Okay, so initially the root, the left, and the right. So have a look at this example. Start with the root. So as I'm going to start with the root, print the root first of all. Then I'll travel towards its left. So in the left subtree, 4 is the head. So print 4. Then again go to the left. 2 is the boss of the left subtree. Print 2. As it is not having left and right chain, go to the right of 4. 6 is headed. So 6, print the 6. If as it is not having any left or right, go to the top. So you reach the root node. There the left root is done, left subtree is done, go to the right subtree. So right subtree is headed by 10, print it. The left of it is headed by 9, print it. As it is not having any left and right chain, again backtrack. Go to the right side of 10, it is headed by 11, print it. As it is not having any left and right chain, job done. This is the pre-order traversal of the given tree. Now in the post-order, the third traversal technique. Left, right, and root. The root comes last here, right? So it is used for the evaluation of any given expression. And any given expression, to evaluate it, the system is internally going to convert it into postfix expression, which is free from all the brackets. The arithmetic logic unit is going to use postfix expressions to evaluate any given infix expression, right? Which goes with this traversal technique, which is left, right, and root, right? So for the given tree, start from the root and go towards its leftmost end, which is 2. As 2 is not having any left child, not the right child, print 2. Then go to its top. It's the left child of 4 is done. So go to the right of it. 6, as it is not having any left and right child, print the root 6. Go to the root now. Print the 4. Because the left and right are traversed. Now 4. Next, as the left child of 8 is done, go to the right child of 8, which is headed by 10. Go to the left of it. 9, as it is not having any left and right children, print 9. Go to the right of 10, which is headed by 11. As it is not having any left and right children, print 11. As left and right children of 10 are traversed, print 10. Left and right of 8 are done, so print 8. So this is the post-order traversal of the given binary tree. Okay, then how to convert or how to construct. Till now we have seen from the binary tree, we have gone to get the in-order, pre-order, and post-order traversal. In the reverse way also you can go. You will be given an Inorder and Preorder, and you will be required to get a binary tree out of it, right? So how we are going to do this is, so we always know that in the pre-order, root node will be taken first. So the first element in the pre-order will be the root. Identify that in your in-order, right? G. Its left elements will be in its left subtree and the right elements will be in the right subtree. That's what I have done. Left subtree and the right subtree. Remember one thing, when pre-order and in-order are given, pre-order is to identify the root, whereas in-order will be used to identify the left and right children, right? Let's go with the next element, B. So within the list, have a look. Where is B? In order, here it is. And its left child is Q and right is K, C, F, A. Do not touch G because G is the root. G is already taken. It is the root. So G acts as a boundary. So K, C, F, A will be the right children of B. Next, the next element in pre-order is Q. So is Q having any left element? No, in order. Coming to right, B is there, but it is already been taken as its parent. It is the parent of Q. So you cannot touch. So we understand that Q is a leaf root. The next element in pre-order is A. Coming to A, its left side is K, C, F. They will be the left child. And the right child, you don't have a right child because G is the boundary line. G is the root of this tree. Right? Good. Next element in your pre-order is C. The left is K and the right is F. Right. The next element is K. K is not having left or right children. B and C are already taken. They are the parent and grandparent of K respectively. So we cannot touch it. Next element is F. Even F, its left is C and right is A. Both are taken. One is parent, the other is grandparent. Next element is P. So the elements left to P is the root which we cannot touch, and the right is E, D, H, R. All four will be on the right side. Right? Very good. Then coming to the next element is D. The left child of D is E and the right children are HR. Coming to the next element, E is not having any left or right children. Next is R. Its left is H. It is not having any right. Next element is H. H neither have left nor right. And there is no more elements in your pre-order. So the resultant binary tree constructed using pre-order and in-order is this one. Okay. Once again, I am repeating, use pre-order to identify the root node and in-order to identify the left and right subtrees. Okay. So similarly, you will be given in-order and post-order also. The same process, but in the reverse order. In the post order, you can clearly see that the root node will be printed last, right? So take the last element in your post order and consider it as root. Check where it is in order, and left children will be in the left side and right children will be on the right side. See 1. So pre-order we traveled from left to right. Post order we are going to travel from right to left. That is the only difference. Remaining story is as it is. So 1, the left children are 4, 8, 2, 5 and the right children are 6, 3, 7. The next element in post order is 3 and its left children are 6 and right is 7. The next element in post order is 7. 7, the left child, if you identify 7 in an order, its left is 3, which is already it is having 3 is already a node, individual node. We cannot touch it. right? And on its right side, it is not having any elements. So 7 is a leaf node. Next element in post order is 6. Even 6. Left side is 1, which is the root node. Right side is 3, which is the parent of 6. So we cannot touch. Even 6 is a leaf node. Next element is 2. If you see in order, the left of 2 is 4, 8 and right is 5. Split it. Next is 5 in post order. Coming to the left of 5 in order is 2, which is its parent. 1 is the root of the tree. We cannot touch them. So 5 is a leaf node. Coming to the next element in post order is 4. So the left of 4 you do not have any elements, but on the right you have 8. Place it. Next element is 8. 8 left side is its parent, which is 4. Right side is its grandparent, which is 2. So even 8 is a leaf node and there are no more elements in your post order. So this is your final binary tree constructed using in order and post order, right? So that was about trees and binary trees. How to traverse, how to construct a binary tree from the given traversals and how to traverse, right? So that is one type of nonlinear data structure. The other is graph. Graph is also a nonlinear data structure and which is having two sets. One is a non-empty set of vertices and next is a finite set of edges. So graphs are represented using a set of vertices and edges. So basically we have two types of graphs, directed and undirected. For example, if you have node A, B, C, D and E, say 5 nodes are there and edges which connect them are like this. So if as it is undirected, say I'm not having any arrows over here. If I claim that AB is an edge, then even I can say that BA is also an edge, right? So the same point, as it is unordered, if V0, V1 is an edge, V1, V0 is also an edge and they are equal, right? What if your graph is a directed one? Something like this. If you have AB, if you say that AB is an edge, then BA is not an edge, right? Because from A, you can travel towards B. There is an arrow indicating that. But from B, do you have any edge? Do you have any edge with A? You do not have. So AB is an edge in this graph. BA is not, right? That is the basic difference between undirected and directed graphs. Okay, so this is how we call these vertices are also known as nodes, right? And in case of undirected graphs, the unordered pairs of distinct elements is the vertices, right? And the edges will be represented like this, or by removing the dashed lines, you can write like this also. The names of the two nodes, one after the other, undirected graphs. Okay, fine. Coming to another variation of graphs is weighted graphs. Weighted graphs are mostly used, you might have seen maps. So from one place to the other place, what is the distance? So on an edge which is connecting these two places, you will be given some numerical value, say so and so kilometers, right? So that is nothing but a weighted graph. Have a look at this picture. A weight of 3.5 is there between Seattle and Chicago. And a weight of 2.5 is there between Salt Lake and Dallas, right? Between San Francisco and Salt Lake, you have 2.5. If an edge bears a weight on it, it is known as weighted graphs. So even you can have weighted directed graphs also. Totally we have 4 combinations, my dears. You can have a directed weighted graph, directed unweighted graph, or you can have undirected weighted graph, undirected unweighted graph. These are the four combinations you can have. Okay, based upon the application, we are going to choose an appropriate graph to represent our problem. Generally, people say that graphs gives you a solution for all the problems in this universe. Yes, you have a look. The basic application of graphs will be, say, your anywhere in your Facebook friend, you'll be looking at few people's suggestions. Do you want to make friendship with them? They are mutual friends to you, right? How Facebook is able to identify that so and so XYZ is a mutual friend, is not directly friend to you, but a friend of yours is a friend to that XYZ. So using Facebook uses a graph based algorithm to identify that. Every social media use that. You take it, Twitter, Instagram. If you are following a person and that person likes a tweet, that will be reflected to you, right? So all these are done or implemented using graphs, right? Right. So coming to DAG, directed acyclic graphs. It's a very important one to understand. DAG is a directed graph with no cycles. So directed, the word, the full form itself tells you directed graph it is, and it is acyclic in nature. There will be no cycles in it. Okay, have a look at this graph. You will not find any cycle in it. Okay, right. Coming to representations of graphs. And graphs can be represented using matrices as well as linked lists. So the graph which I have taken is a undirected graph, unweighted graph. So if there is an edge between two nodes, I'll represent it with 1. If there is no edge between two nodes, I'll represent it with 0. As it is undirected, if there is an edge between 1 and 2, I can claim that there is an edge between 2 and 1 also. So this will be symmetric in nature. Symmetric in nature. And you can see that there is no loops over here. That is, there is no edge starting with a node and ending with the same node. So the diagonal elements are filled with zeros. Okay, so this is how I'm going to write the adjacency matrix of a given unweighted, undirected graph. Okay, right. So in case of weighted, directed graph, adjacency matrix can be written. And you can see that, say for example, 25, there is an edge between 0, 0, 1, 2 index values, guys. Or if you want, let me represent with the values of my nodes 1, 2, 3, 1, 2, 3, right? So there is an edge between 1 and 2. So I have represented this column with 25. There is no edge between 1 and 3. So I have represented infinite. Why infinite is, right now there is no direct edge between 1 and 3. But there is possibly a path. Say, you can travel from 1 and 2, 2 to 3 and 3 to 1, which is 25 plus 10 plus 5, which is 30, 40. You can fill in the future this infinite with 40. But right now, adjacency matrix will be filled with the direct values. So I have taken infinite. Then why zeros as diagonals? If I consider 2 as it is not having any self edge and it can never be formed in the future also, I have represented it with straight away 0. Okay. So this is the adjacency matrix for directed weighted graph. Right. Coming to representing these undirected directed graphs using linked list. If there are few edges and number of nodes are high, our matrix will be sparse in nature. To overcome the disadvantage of sparse matrices, I can use single linked list also. So have a look at this one. So a list will be taken which will hold all the names of the nodes or vertices, and a linked list followed to it to link its neighbors and each node will hold the neighbor name and the next node's name. Okay, and the last node will be filled with its next part with a null or nil, saying that it is the last neighbor. Okay, this is how we can even represent a graph using lists. Okay, so this is a representation of weighted directed graph. The enhancement will be as the edge is also bearing the weight, you need to hold the value of the weight also. So the structure of the node changes. Previously, we were having the structure of the node as neighbor and address of that neighbor. This were the two parts, right? Now it will be split into three parts: neighbor, weight, and address of the next node. So three parts will be there in case of weighted ones when weight comes into the picture. Okay, so this is how we are going to represent a graph in case of directed weight. Okay, yes. Then what are the applications of graphs? As I said, in computer science, every flow of computation is a graph. If you think like a compiler or an interpreter, you can see how with every function call, the return address is stored and how the control is moving from one function to the other function until unless the process stops is nothing but one of the major applications of our graphs. Second is Google Maps. Just now I have said, right? So if you want to travel from Hyderabad to Delhi, there will be n number of ways. N intermediate places will be there. Stops. You cannot directly travel if you are going by road. Then you cannot travel straight away. You will not have any displacement. You just have distance, right? So intermediate stops will be there. What are those stops? All possibles Google Maps will give you. That itself is a graph. Coming to the Facebook, as I said, in Facebook runs friend suggestion algorithm to show or suggest you mutual friends, right? Then comes operating systems. So resource allocation graphs are used for resource allocation, right? So where resources are considered as the vertices of our graph. Right? Edges will be used for allocation of these resources to the system, right? So this is how in various ways graphs are used. Guys, if you look in around of yourself, you can figure out that every problem of your life can be resolved using graphs, right? So with this note, I'd like to conclude that there are two basic nonlinear data structures. One is trees and the other is graphs. And basically we work with binary trees. Guys, do follow my next video also, where I'm going to go in depth into the concept of trees, where we are going to learn about what a binary search tree is, what is an AVL tree, right? How to construct them and all. Do follow me. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.